everyone! Hope you're all having a fantastic beginning of 2018. Mine started with cleaning my hard drive. And I discovered actually quite a few research files I did last year, and one of which I thought might be very interesting to you as a small VEX exercise, which also produces quite beautiful visual results. So I guess a bit of a backstory is in order. I was fascinated with religious patterns at that time as a human compression mechanism of the surrounding world. And I don't know how exactly, but I ended up reading about emergent behavior. And I think it was a talk by Stephen Wolfram where I saw cellular automata patterns. So, of course, I had to play with it. And I discovered a very curious thing. So, for those of you who do not know what cellular automata is, I'm going to show how it works now. So the idea is very, very simple. Imagine, and for right now, we're going to just look at 1D cellular automata. And imagine you have a row of pixels. And we're going to say that it is a step number 1. And let's give them some values. So let's say this is going to be 0, so it's just going to be gray. Let's say that this is going to be 1, this is going to be 1, and everything else is going to be 0. So in cellular automata, we have rules that define what we do. And what we usually actually do is we look at every single pixel and we look at its direct neighbors. So if there is no neighbor, usually it's considered black or 0, because cellular automata is binary. And you have very specific rules for what to do in every case. So let's say we have a couple of rules of our own. Let's say that if we have 3 blocks and one of them is going to be white on the very right, we want to produce a white block. And what that means is in step number 2, and let me copy the template of this row. And what will happen now, when we look at this particular pixel and we're looking at its neighbors, we are kind of going back to our rule set. So here's our rule set. And we are looking, so we have exactly this arrangement, and here is the rule. This pixel is to become white, next step. And so here we say, okay, now it's white, and we just move to the next pixel. So here is the next pixel, and it has the following arrangement. So let's create a rule for that as well. So if we have this arrangement, then let's say it's going to be black or gray, 0. And of course, in the step 2, we will just put 0 here, so we're not going to color it. And again, we're going to check this one. So let's say for this one, it's also going to be just 0, and all these ones will become white. So let's imagine we have all those rules. And what we do next is we just, as number 3, we just continue. We just repeat and repeat this. So where's my template? So we repeat this as many steps as we want. And with 1D, usually people stack these rows on top of each other. So just to show you an example, and by the way, all the rules are even numbered for cellular automaton. So for here, for example, rule number 30, as you can see, so let's actually open it in full resolution. You can see that we have all these rules here, and come on, Pinterest. And it says us what to do. So we have this, for example, arrangement of 3 white or zeros in this case. It will also produce a 0. And you can see what kind of pattern starts to emerge if we only start with one single one-value block. And there are a lot of very beautiful patterns that emerge from this. So you can see it on Wolfram Math World, and they describe all the rules there. I'm pretty sure it's also on Wikipedia. But now I will tell you what I discovered while playing with it, which I found extremely curious. So, oops, I don't want it white, I want it gray. So let's imagine that we have a grid. So I would need to copy my template again. So let's imagine it's not a 1D cellular automaton. Let's imagine it's a 2D, so kind of like an image with pixels. So yes, something like this would be fine. And I was thinking, can we actually increase how many neighbors we are checking? So for example, if we are checking this particular pixel somewhere right here, can we actually alter how many neighbors we can check? Because we have so many options. We can only check this one, so these 4 neighbors. We can also check all the 9 neighbors. We can check 18 neighbors, and so on and so forth. So, and it kind of will be determined by the radius of where we check. So imagine like if this is the center of our circle, we can draw a circle, which is probably going to be super Ori. Yeah, I think it's fine. Well, you can imagine it's a perfectly nice circle. And we can check all the other blocks inside that circle. However, now we get exponential complexity because just with only 3 block arrangements, when we had it with 1D, we had to describe every single possibility of what can happen. So we had to describe what if everything is 0, what if everything is 1. We had to describe what if only 1 is 1 on this particular location. So we had to come up with a lot of rules for it to follow, and you can imagine how much more of them will be if we have to check, let's say, 25 neighbors. It's just going to be too much for us physically be able to, well, we probably can code it, but it will take us a very long time. So we're thinking how we can get around that. And what I came up with, if I can, okay, I'll just leave the scribbles because I think I made everything in one layer. Oh, no, not really. So 1 second, I'm just going to copy this again. And I'm actually now going to draw in a new layer. So let's say we're still checking this pixel here. And we have this parameter of a radius. So we can tell how big of a radius it can be for us to check for other blocks. And in order to be able to not come up with all of this crazy amount of rules, I decided to go with something different, and I decided to go with accumulation instead of just straightforward rules. So it is an accumulation algorithm inspired from cellular automata. So we have the radius parameter, yes, and we also have the accumulation. So let's imagine the following case. So let's imagine we're checking our guy here in this particular radius. So we're only checking for 4, or 9, let's say it's 9, let's say that the ones that are partially inside are also considered. So let's say we're checking for this 9 neighbors around because this is our radius that we set. And let's say a couple of them are actually already have values. So let's say that we start with these guys being 1s. So what we do in our algorithm, we cycle through every neighbor and we record how many non-zero ones we found. So we actually record, so we get 1 plus 1, and we realize that we found 2 of the guys that already have their state as 1s. So let's mark them as 1. And in this case, it's going to be a float 1. And that kind of comes back to the accumulation algorithm, because now, knowing that we have 2 of them, we're going to assign a new value. So this new value will be exactly this 2 divided by our division parameter. And it's going to be a new parameter that we're also going to control. So division. And the reason we do it, so let's say our division is, I don't know, 5, meaning we're actually going to only assign this new red pixel a value of 0.4. And the reason we do it this way is because we want this accumulative effect. And in the next step, it is very likely that this guy will receive another 0.4. And then again, it will receive a 0.4. However, as you can see, if we will continue this infinitely, at a certain point, it will just become too much. It go to infinity, and it will just the whole of our board will become black or white, black. It's hard to tell. Basically, it's all will be filled with the color we choose as 1, because we're going to clamp it as well. So we're going to clamp all of our additions. So we will end up with this case, everything just becoming absolutely white. And that is also what not we want. And that's where we come into next parameter. This is going to be neighboring count, NAC, or I will call it NAC, but it's a neighboring count, which tells us how many neighbors we are actually considering and when are we going to stop. Because if we don't ever stop, everything will become with a value of 1. So we say that, okay, we only want to consider if we have less than, let's say, 3 neighbors. And that means that if, for example, we had these guys as white already, and we were checking our red, so let me erase the value we already put in here, and we were considering this red pixel, it would start counting how many of non-zero neighbors it has, and it would see that it's actually a 4. And 4 is bigger than 3, meaning we will not do anything to this pixel. And this way we kind of encapsulate a lot of rules in just 3 parameters that we can determine and play with, rather than writing rules ourselves explicitly. We kind of hope that these 3 parameters will allow us to create a big variety of patterns, and indeed it does work. So now let me show you how you can implement it in Houdini. So here we are inside of Houdini. As you can see, this is already a finished one which I was playing with when I initially wrote it. And as you could see from the examples I shown before, and from here, it can create so beautiful patterns. And just to give you a quick sneak peek into what you can do. So here I only expose the distance, which I probably should have exposed more parameters, which we were talking about previously. But since this was a kind of a very quick mashup of ideas, I didn't really care for the code to be pretty or functional. Well, it had to be functional, but you know, I was not really thinking about exposing parameters. A lot of things are just hard-coded. But as you can see, just by changing even the distance, we can get a variety of patterns, which is just so beautiful. But anyway, I will stop spoiling things and we'll just create a new one. Let's do it together. So we should start with, and let's hide other object. So what do we start with? First of all, we need the image, so to say. So I will just create a grid. And let's not give it any divisions yet. Would this size be enough? I think let's make it a bit bigger. Let's make it like 30 by 30. And now let's divide it. So we will tell what is our density, so to say. And I think 0.1 should be enough for us. So we're going to get a lot of pixels. As you can see, we have 90,000 primitives. And now we need to somehow initialize it, because as you can see, and by the way, in this case, we're actually not going to treat primitive as pixels, we're going to treat points. So in that case, we actually have 90,601. As you're going to easier to write the parameters to and to do point lookup. But now we have to just initialize some values, and I usually like to take a circle, and we will get a wrangle, and we're just going to say, we will call it initialize. And the circle itself, we want it to be a polygon. Let's start with just 4 divisions. So, and we want, of course, to be on XZ plane. And it also only has 4 points. So what we're going to do is we're just going to tell to have black points where there are points of the circle, which we can easily do with VEX. And we can just say that we want to do a small point cloud lookup. So we're going to say point cloud is, and it's going to be an array, PC find. So we're going to look at the input number 1 of the circle. I want to look at from the current position we have, so at P, just a very small radius. We only want to find 1 point if possible, so we're also going to put only 1 here. 1 holds the maximum amount of points we will put in our array. And now all we want to say, if the length of our P cloud is not 0, so if we actually found something, we want to have state. So we're going to say f state, and we're going to just assign it 1 right away. And we also want to visualize this, so we're going to say that our color will be black. So in this case, if it is, if we have value of 1, it will just be black. But of course, you can invert it or make any other color. It doesn't matter. So as you can see, we have our, oopsie doopsie. We have our 4 black points right here. And now we can start putting a feedback loop. So we want to say for each loop, with feedback. So we want to do it by count. We want to feedback each iteration. And for now, let's just put 1 feedback loop. So, press it back. And I have just realized that I'm still on 16, Houdini 16 at home. Should probably update. But you should have the same options, even if you are in Houdini 16.5. So, inside the loop itself, we will of course need a wrangle, where all the magic will be happening. So we will call it magic. So now we will run over all the points. That's exactly what we want. And we want to get our neighbors. So let's create an array for that. So neighbors. And we're going to use again a PC find function. So we're going to actually look in the same file. We're going to look from the position we have. We need to have some kind of a distance. So we're going to float lookup distance. And we're going to create a channel for it. Just going to say look up distance. And we're going to we will have a couple of controls. So I'm just going to comment them out right away. And here I'm just going to separate those. So in here we will finish our PC find function request. So we need this. We will put our lookup distance right here. And how many neighbors do we care to find? Well, it depends on how many you have in mind, but I don't think we ever want more than 100, so I'm just going to put 100 right here. Yeah, but you also can expose it as a parameter. So now we want to see what states our neighbors have. So we're going to say find how many non-zero states neighbors we have. And after we know that, we want to accumulate results. So is it actually with double C? Yeah, I think it is. Sorry if it isn't. Accumulate our results. So that's just all the steps really. So first, find how many non-zero states neighbors we have. So what we're going to do, we're going to iterate through all the neighbors. So in that sense, now I'm thinking, do we actually ever want more than 10? Well, technically, it depends on the radius. Oh my god. Okay, I'm going to leave 100. It's probably very inefficient, but well, because now we're going to iterate through every neighbor. So int n in neighbors array. So now it's going to take and create an integer n for every item in our array neighbors. And in here, we just want to write a simple if statement. So if point 0 state n, so we are querying what is the state of our neighbor, and it is not a 0, so not equals to 0. And, very important, n is not equals to ourselves, so we don't want to check ourselves. So don't check ourselves, because in the point lookup, you just give it a position, which means it will also include the point from where we are doing the lookup. That is why you really have to exclude it this way. And here we can just say that we want to tell that we found them. So we will need to create an integer, but first we will say that we found something, and it's going to be an integer, because we don't care exactly for the values of the state. We just care that they are not 0. So here we just say that found is 0. So we start with no finding nothing, and then we just every time we're going to encounter something that is non-zero, we're going to add 1 to our integer found. So now if we found something, so if found is bigger than 0, so unless we don't want to do anything, if there is nothing around us, unless maybe you want to actually do something, but in my examples, I always made this a rule. So if found is bigger than 0 and found is smaller than, now we want to say how many neighbors you want, so nays count, and it's channel maximum neighbors. And actually, I will also rename it as maximum neighbors. And just gonna equals. So if that is true, we want to modify our state as well. So we want to say that our state is equals to found, so how many non-zero we found, divided by, again, this division and this division parameter I was talking about. So we're going to say it's called division. And we're just going to say it's a division. And since division is a float, we are dividing by float, so in the end we also should get a float. So now we also want to visualize it somehow, and we want to say that our color is, so again, as you remember, we want to clamp it. We don't want our color to exceed 1. So we're going to say that we want to clamp our state between 0 and 1. And we also want to invert it, because if, as you remember, with 0 we want white background, and with 1 we want black background. So it would be the kind of inverse, so I have to invert it here as well. And that is actually pretty much it. So let's apply and accept. And it's actually complaining an implicit cast. Is it because of the... Oh, Yeah, of course, because we need to put I here. So now it's not complaining. We want to create all of our parameters right here. And so let's set up our lookup distance. So let's start with something not too big, like 0.2. Divisions, I'll put just 2 for now. And maximum neighbors, I'll put to 3. And as you can see, we have accumulated some results around these black points. So these points all around, unfortunately, I cannot just, oh, I can switch. Good. So as you can see, we have this lookup distance. So if I decrease it, we have less points that were affected. If I will increase it to something like 0.9, as you can see, it's like as if this was the point where we created this lookup. All around it, we have these points that were affected. And all of them got very simple 1 divided by 2, so half. And if we check, I think we have to see that their state will be half. Yeah, as you can see. So if we would put our division to 4, it would be 0.25. So very logical. And I will put my lookup distance back to something like 0.2. So these points were affected. And it's very simple. But if you start to feedback through it suddenly, so let's take a second and fetch feedback. So I'm not seeing an update actually from... Oh, I found a small typo on my part because it is an accumulative effect. Right now we are just overwriting the state every time, and of course nothing gets updated. So it has to be plus equal because we are accumulating the effect. So now if I apply and accept and we place the feedback, as you can see, we have something emerging. So let's actually let it run for more iterations, and right now it's actually accumulating very fast, so I might actually make the divisions like 5, and we should also make more iterations, so like 50. And let's try a different lookup distance. So yeah, as you can see, just by changing the distance, we get very different patterns. And some of them are very, very beautiful, but it takes some time for it to calculate all the points. So as you can see, oh my god, this is just one really nice. And again, we can decide the division. So in this case, let's just make 2. And by the way, if you want just a binary pattern, you can just not have any divisions. So this one looks almost binary, but I don't think it actually is. I think we would have some states that are not exactly 1. Yeah, so 0.5, so we still have them. So yeah, it kind of determines how many shades you want. But yeah, and we can also check how many neighbors you want. So let's say if you want actually 4 neighbors. As you can see, our pattern starts to change. So let's something like 0.015. Oh, everything just became black. I think it's because we are considering a lot of neighbors. So let's say we want to consider only 2 neighbors. Ooh, hello there. That's very nice. And let's actually add more shades. I don't know. I really love playing with this and seeing what it can come up with. And it's, I don't know. Doesn't it really feel to you like magic? It's just something so simple. Like literally, look at this code. It cannot get any simpler, and it gives us so much variety of various patterns. I don't know, I found it absolutely fascinating. Another thing you can really play with, and let me actually get some kind of a... Let's try 35. I don't just random numbers, but it also depends, of course, on your grid divisions. Right now we have 0.1. So yeah, this is quite nice. And I will actually not put only divisions as 1. We will just get a binary pattern. So there it is. And what you can do as well is not have just 4 points. So let's say if we start with a lot of points. What if we just start with a circle and make it super big? So more divisions, please. Thank you. And now if we run it, of course, this will always stay as 1. So you kind of burned this pattern into your overall canvas. But oh my god, look at this. It's so pretty. So now I can show you how I actually shaded it. It's very simple. I just use the ramp. But just in case you don't know about ramps, so let's first make more shades. Otherwise, we wouldn't be able to color it with more than 2 colors. So let's say that our divisions are 5. It will take a while. So yeah, we have now this beautiful, beautiful pattern. And as a way I would color it, so again, VEX, always VEX. So coloring. Actually, now that I think about it, it would be really cool to print it as a coloring book. You know, I've seen some very cool books on mandalas where you can just like meditatively color it. So yeah, we can actually make a procedural mandala book. I think that's actually a good name for this tutorial. Procedural mandalas. Anyway, I'm going off the topic, so let's do the coloring. So the coloring, as I mentioned, is just a ramp, and in that actually case, I'm thinking of bringing the one I already have, just because I already established very nice color palette there, so I'm just going to copy it. But I'm going to explain to you all the code, one line of code that does the coloring. So as you can see, here is our colors. So all I'm doing here is I'm just saying that I want to color it based on our red channel. And why am I taking the red channel? It's because all of our red, green, and blue channels are currently the same, because we, as you know, we have just gray. So we just copied it in our vector of 3 items, and every single item in that vector is the same value. Therefore, it really doesn't matter which one you take, red, green, or blue. And I want to say is I want to tell it to color from 0 to 1. So this red channel is responsible for what color we are sampling from this ramp right here. So which means that all the state 1, so if you remember, we had black parts here. As you can see, they all became blue right here. And everything that was 0, which previously was just white, now it became black. And everything in between all those shades, that's why this parameter of divisions is important if you want to shade things. So let's actually put a 10, because you can pick up on more shades in your ramp. So now it will recalculate. Yeah. So now it hasn't even finished the middle, but maybe it's what you planned for. And as you can see, you can make a difference. So let's say that I wanted red to be here, and actually I want the red to be here, blue to be here. So you can really change the coloring as much as you like. But the shades themselves, they are very rarely just in the middle, so it's kind of a bit hard to control sometimes. So mostly just will have a dominant color, which in this case will be blue. And I'm just putting like warmer colors as decoration elements. So yeah, and what else can I advise? Yeah, just don't put one circle, put multiple circles, copy circles and circles. That's what I did. So copy 2 points, and I just copied another circle, copy the circle, circles everywhere. So I don't want it as it's a polygon. Let's make it smaller, less divisions, 9. And I don't want it to transform. And we make this one smaller too. So if we now init, as you can see, we have this very nice pattern. So you can kind of make a pattern in advance and populate that. So let's make this one bigger. So let's say we have already this pattern, and this is our starting pattern. And now if we run this algorithm, it's just going to fill all the in-betweens, so to say. So let's see what that looks like. So yeah, it actually didn't have enough space to fill because, as you remember, we limited how many neighbors you have. And since in this places it already had 2 neighbors, nothing was happening. And that's why you sometimes want to put a bigger number here. So let's say that our maximum neighbors is 8. Wait a bit. And as you can see, we now have, oh wow, something very complex emerged. And I'm actually quite curious if we color it. Well, it kind of looks a bit like almost noise. So not all of the patterns will be, how do I say it, not noisy. It was perfectly interesting order. But as you can see inside the thing, actually, you get a very nice fillings. And this, I think, an algorithm is very interesting because you can just use it to fill certain elements if you're making some kind of a, you have already existing framework for your pattern and you just want to fill it. I think it's a very interesting algorithm. And part of me that is kind of very curious about this type of algorithms is it is so very similar to some of the patterns that were made by humans thousands of years ago, and it just blows my mind a bit. But I'm not going to speculate on this topic. It's a very vast topic, and I'm now just wanted to show you how to do this small but fun VEX exercise. And so yeah, I hope it was informative for you, that you will have a lot of fun with it. And so let's try something else. I'm like addicted. I want to see. And it doesn't, by the way, have to be only the kind of mandala patterns, as I showed you in the beginning, if you remember the strips of patterns. So I think division 5 should be better. But yes, you remember I showed you like the blocks of patterns. So let me see if I still have it somewhere. Scrolling. Yeah, so this one's It's kind of like my research doc. But yes, you can see this ones. It's the same algorithm that I showed you before. And you can create these nice strips, this very beautiful mandalas. Like, oh my God, look at this. I can't help. I see faces here. Like my object recognition in my brain just instantly labels it as a face, which is kind of funny. But yeah, so hope you had a lot of fun. Hope you will have even more fun. And happy new 2018. Bye bye.